Hey there, everybody, and welcome back to class. How are we doing today? Starting to get a couple more folks trickling in the room because we're moving back to science and away from that test review. Hey, Adam and Rochelle, what's going on? Oh man, Chuck is busting out some puns. I have a hunch that might keep happening. That actually might keep happening throughout the whole session. So yeah, you got Adam Thermo going on. So the cool thing we're doing today is we are going to talk a lot about what was covered in Thermodynamics 1. I do see a couple people that were here for Thermo 1 about last week at some point, I feel. So welcome back to the second installment. We will now mostly talk about applications and what this stuff looks like, and do, most importantly, a bunch of questions that really talk about it. So the main thing we're going to do today is really talk about all the concepts covered in Thermo 1. If you have not covered Thermodynamics 1 channel class before, if you've not studied Thermo in a while, if you are brand new to Thermo in general, this is probably not the best place to start, just to be totally honest with you. And so we're going to mostly apply the stuff we know, and so do have a heads up, we do want you to have basically a basic foundation. You don't need to be an expert by any means, but really do have kind of the foundation set. Cool. And so what we'll do is we'll use the foundations of what we know in terms of adiabatic, isothermal, isochoric, etc., and how it applies to engines, refrigerators, and then go through some questions. That's the main idea for today. So in order to really talk about a lot of this stuff, though, I don't even really want to talk about this yet. Let's first talk about the main ideas that we'll be covering. Let's discuss the differences between adiabatic, because that'll be the main focus today, adiabatic versus isothermal. So let's discuss these two systems. What makes an adiabatic system adiabatic? Like, what's that mean? You got it. So no heat enters or leaves that system, which is exactly true. As you could say, Q equals 0. So now what's the formula, though, that we would use to relate Q to the other things here? What's the master formula that we're going to really talk about a lot today? The formula of thermodynamics. You got it. So your internal energy of the system, I'm going to define it as the change in internal energy, is equal to Q minus W, but you got to tell me, what's the formula for work? What is work? P delta V, exactly. So you got it. So yeah, you got it. So, well, the thing is, you can also say displacement, force times displacement. I agree, Adam. It's actually the same thing, though. Whenever we're talking about gaseous systems, though, the way that we talk about that actual force and that displacement, of course, is by compressing or expanding. And so work deals pretty much with two main things. You have compression, you have expansion. So compression versus expansion. So let's talk about this for a second. So now I'm going to draw some pictures. And I know if you guys were here actually last week when I was having the tablet issues, it worked fine all week, literally until right before this class it broke again. I think there's something with thermodynamics that breaks my tablet. Like, it was seriously fine all week, and I was just like, are you for real? I know it's going to be the same people coming back. They're going to think that I just didn't ever fix it, but it literally just stopped working again. So I apologize. I'm going to try again, see if nope, and it works again. Awesome, it just fixed. Magic. Seriously, Chuck, look, I can draw pictures again. It just fixed itself because I complained about it. Sometimes that's how the world works. It doesn't fix until you really complain. All right, so that's by the system right there. There we go. That was actually really, you were bad luck and it just became good. I don't know what it is that is going on with it, but it's back in business. So what I'm going to do is talk about a couple different things in terms of pictures, and this will really kind of set the tone for what we're going to cover this whole system. So I'm going to call this thing the system. So the one thing you got to be really careful with whenever we're doing any of this, you have to define what the system is. And so now I'm going to draw two different force vectors because Adam brought this up. When we talk about work, we often talk about displacement and force. Oh, it stopped working again. Dang it. All right, so all right, I'm giving up. I'm just going to buy a new one. It was good all week. So I'll draw some vectors this way. I'll draw red vectors like this. And then I will also draw some blue vectors like this. And so now if I were to compare these two vectors, one of these vectors would be showing the force applied by the system. The other would be showing the force applied on the system. So which is the vector showing work or force by system, blue or red, which is by system. Blue, exactly, you got it. So like that's kind of the straightforward thing. But so what I want you to notice then is, like we said before, and I'm just doing this because Adam brought up the force and displacement thing, and I want to show you that, yes, it is the same idea. So notice if this is the force, and this thing was displaced as such, What is true of the direction of force and displacement? Is it the same or is it opposite? So note, like, watch. Actually, it might help. I'll do it this way. I'll just go one-sided, so we don't have to think in multiple dimensions. We'll do a single dimension. We'll just look up versus down. So notice what we did before. The system started off like this, is we said through some kind of thermodynamic process, this just happened. So which way was the system displaced? Up is, yeah. So then if you have your force and your displacement going in the same direction, what is the sign of work? That's positive. You got it. If whether you call it negative times negative or positive times positive, you're going to get a net positive number. So notice that if you're defining this in terms of the work done by that system, if the system is expanding, well, work done by the system is pushing outwards, and the displacement was also outwards, so you would call that work by system positive. Does that make sense, first of all? This is going to kind of set the tone for a lot of stuff we talk about today. Awesome. Yeah, so it works both ways, too. So we could also say, let's do the same thing. We'll start back at our starting point so we can talk about it. So let's say that we just had this displacement right here. Squishes down really small. So then what was the work done by the system, positive or negative? Exactly, Adam, right? Since the force, the work done, or the force applied by the system is upwards and displacement was downwards, if you ever have a force and a displacement in opposite directions, it's going to be negative work. Exactly. So notice that you would say expansion is positive work done by the system. Compression is negative work done by the system. But if you wanted to be weird, you can also talk about this in terms of work done on the system. So the standard is by, and so I do want you to be aware that this is like, for the MCAT, it's almost always defined in terms of work by the system, so I'm doing by first. But you could also say work done on the system. So if we had this compression here, what would work done on the system be, positive or negative? So for compressing, what's the work on the system, positive or negative? Navina, Nicole, you got it. So think about the vectors, right? So remember, this is all just force and displacement. It's the same thing from our intro physics. So if we're defining this as work done by the system, remember, oh, let me undo that. Sorry, I didn't mean to disappear that box. So remember, this is work, I believe I said on the system. I hope I didn't accidentally say by one of those times. But remember, the blue arrow is the work done by the system because the system can actually push up against its surroundings. So the red arrow is pointing down, that's the work done on the system, right? Because that's like us pushing on the box. And so if you're defining this as the force or the work on the system and you displace it downwards by compressing it, then you say work on the system is positive. Does that make sense? We had a little bit of mixed answers there. So if you define it as work on the system, that's the thing. You can define it as either on the system or by the system. You got to be careful with whether you're talking on or by, as Adam brings up. That's what it's all about. And so you got to read the answer stems and the question choices very, very carefully, as Rochelle says, because if you're talking about on or by, your answers are always going to be opposite. Like positive work on the system is by definition negative work by the system. And positive work by the system is always negative work on the system, right? Because you're changing the arrows. And if you ever change the arrows, it's like gravity, right? You can define up as positive or down as positive, but no matter what, if you're talking opposite directions, you're going to get a negative sign. How do we feel about that? That's, I think, one of the most conceptually complicated concepts, and I want to get out of the way right now. Thumbs up. Okay, cool. So we're not going to get too much into this. What we're mostly going to do now that we have the idea of expansion compression, we're going to talk about adiabatic, isothermal, and then we're going to apply it to our engines and all that kind of stuff. And so we said already, and we'll get this out of the way since you guys already discussed it, adiabatic means that there is no heat entering or leaving the system. So adiabatic effectively means Q is 0. So if you do have some work being done by the system, right, expansion, what's going to happen to your internal energy in an adiabatic expansion? Get this out of the way. So if it's work done by the system, right? So remember, expansion, is that positive work by the system or negative work by the system? Then it's positive work, exactly true. So if we make this sign positive, notice how we've got a negative, we're subtracting in front of it, thus your internal energy will Decrease. You got it. So now I want you to think about this conceptually, though, because if you really approach therm from a more like kind of real world life example concept, it makes more sense. You have two main things when it comes to adiabatic processes. If you're, and this is actually true for isothermal and adiabatic, if you're not changing one, you must change the other, because all we're going to talk about with adiabatic and isothermal is compression and expansion, right? So there is work every single time. So if there's no change in Q, if there's anything going on with W, it's got to affect the delta U, it's got to affect temperature. Conversely, isothermal, and this, I know this is from the thermal one, so I'm just assuming it. Remember, you have a direct relationship. Any kind of change in temperature is directly proportional to a change in internal energy. So that's just a major concept discussed in thermal 1. And so if you ever have a dramatic increase in volume, right, it's expanding out, temperature's got to drop. Conversely, if you compress it down really tight, temperature has to get very hot if it's adiabatic. Because if there's adiabatic, there's no heat going in or out, so you must change the temperature. Because looking at the equation there, any change in U, there's only one thing you can affect, and that's the delta U, which is temperature. Now, conceptually, and Trick's got the actual formula, is to think about it in terms of molecules, right? So internal energy is temperature. And internal energy is the vibrations, the oscillations, the collisions, all the crap and all the movement, all the energy going on with every little gaseous particle. So if you take all the gas particles in a room and you compress them down to a tiny point, how energetic is that tiny point going to be? Very high or very low? Super freaking high. Yeah, you take all the gas in a room and compress it down. That's like an explosive little bundle now, right? And so if we're saying it's high energy, that by definition means high temperature. That's the big thing, is the relationship between the two. So, and also, do you guys know what the keyword is to know that it's adiabatic other than adiabatic or no heat enters or leaves? There's another keyword to look out for. This is covered in thermal 1. Yeah, rapid, fast, quick. Exactly. Something about it quickly happening. So if you ever have a rapid compression, that thing's going to be crazy hot, crazy quickly. In fact, that's how, I don't know if you guys are into like survival skills, but there's actually a way to start a fire in the woods with like a little, it's like a compression tool where they actually make this little plunger. You put little like cotton and dirt, or not like, you know, sticks and stuff at the bottom, and you compress it really quick, and that compression actually heats the wood enough to ignite it on fire. It's like the way, you know how people basically rub sticks to start fires? It's another way to do it. It's like an old school thing. You just have this plunger, you go real quick, and it just ignites it. I forgot what they're called. You could look them up online, but it's like a primitive skills thing. You can make them in the woods if you're, you know, Bear Grylls kind of person. But super cool. But it's the same idea. It's adiabatic, super fast compression, high temperature. You can even start a fire if you're quick enough. Other way around, right? Super fast expansion, things get very, very, very cold for the same reason. All right, so now isothermal, on the other hand, in an isothermal compression or expansion, we said the temperature can't change. So let's rework this equation real quick. Then all we're going to do today is basically apply these concepts. And so that's why I do want to make sure we're all comfortable with this first and foremost. And since we haven't taught this class in about a week, it's good to do a review. Yeah, fire piston. There we go, Adam. That's what it's called. So if you want to look up fire pistons, it's taking advantage of adiabatic compression. It's pretty cool. All right, so let's talk about isothermal. So isothermal, we said that there is no change in what? No change in temperature, exactly. I'll move this over here. All right, so in isothermal, there is no change in internal energy. So no change in delta U or thus temperature. Same thing. So if you're not going to change temperature, what is going to change? So if we get that out of the term, if you have compression or expansion, heat's got to change, exactly. So in an isothermal expansion, what's going to happen? Will heat enter or leave the system? So in isothermal expansion, you got it. Heat must enter system. So heat enters, whereas in isothermal compression, then heat will leave. The way that I'd like to think about this, I don't know if you guys, there's a lot of different ways to think about this, so I'll kind of just describe different processes of thinking about it. In an isothermal expansion, what's happening is that, generally speaking, if you have a system expand, it gets cold. We just talked about that. So in isothermal, you're not letting the temperature change. So the only way you can have a system expand and not get cold is by actively pumping heat into it. Same thing the other way around. If you compress a system, it's going to basically get really hot. And so if you're going to compress a system and not let it get hot, well, it's got to let heat out or it is going to get hot. So that's kind of like the deal with isothermal. It's like a slower process. You're letting it equilibrate and give off heat or absorb heat in order to not change the temperature inside. Cool. Got some oohs and ahs, so I think that's making sense now. I want to do a quick check-in before we move on to engines and stuff, but this is kind of the foundation for everything we're going to do with engines. And if we got isothermal and adiabatic down, why expansion compression has different either increase, decrease in temp or heat or whatever it is, we should be pretty good to go. All right, I take silence as a thumbs up. If you do have questions, hit us up in the Q&A. Remember, we got 3 teachers in the room. We're here to help. Let us know. We can talk shop, as I like to say, if you want. All right, so let's move on. We'll give lots of examples of this, but we'll kind of do it now in context for the last 45 minutes of class. All right, so Carnot cycle, this is a heat engine. Just as a heads up, this is any old anything. Like it's a car engine. It's just an engine in general. It's just like basically a way that we basically make stuff move. And so whenever we're talking about any kind of thermodynamic processes in general, you have to define the system. So like they will tell you what the system is. And in this case, the system is almost always a gas, but it's the gas inside the pistons of a car engine. And so this system is going to basically be absorbing heat, giving off heat, compressing, expanding, all that kind of stuff. And then that affects to get the tires of the wheels to spin. And so let's kind of define all of our different terms right here. This is the heat source. Basically, this is your combusting gasoline is the left. That's the delta, the T right there. So this is your basically burning fuel. It's where the heat's coming from. This work right here is the tire spinning. That's the actual energy running out of this. And then what do you think TC is then? If you look at the arrows, we can kind of see it. So we have this heat source. Part of it goes in the system. Part of it makes the tires spin. Parts goes TC. With coolant, that makes sense, Grant, but think something more structural. Think energy, right? We're putting heat into a system. Part of the energy makes the tire spin. Part of it goes somewhere else. Where does some of the energy go from a car? Coolant kind of makes sense. That's true. We're not going to get into coolants, though. But that would be more about, yes. Actually, coolant would make sense in that context. That's a good point. I'm just thinking more big picture, like any engine. Not necessarily ones that are cooled. Where does some of the energy go? It's just the exhaust. Honestly, it's just the exhaust pipe. Yeah, there we go. Exactly where you got it. And so it's like some of the energy is going to go into spinning the tires, but part of the heat is going out the exhaust pipe too. Like here's a heads up. You never get 100% pure conversion of energy to energy. We always lose a little bit of energy in the way. So like there's no such thing as a perfectly efficient engine. Like it does not exist. In fact, efficiency for cars is abysmal. If you were to look at like an old muscle car from the the 60s, 70s, 80s, stuff like that, do you guys know around what efficiency those things have in terms of conversion of fuel sources into energy, of kinetic energy of the car moving? Yeah, it's like about 1%. Like about 1%. Like 1 or 2 maybe. Horrible, horrible efficiency. Even like brand new spanking cars that are all gas efficient and awesome, they're still like maybe 20% efficient, like really low. And this is talking from a thermodynamic perspective of the energy contained in the molecules of your octane or whatever gas it is, and how much of that conversion gets converted to kinetic energy of the car moving down the street. So cars are very inefficient systems. I don't know about electric cars. I haven't researched that. I have a hunch they're more efficient, but I just don't know because, you don't need to know for the MCAT, so I don't really know. But they are very, very low, as a heads up. There's very few highly efficient systems. All right, so let's talk about the general processes and how we move energy from this heat source into both doing work as well as partially exhausting. And it's through alternating systems of isothermal expansion, compression, and adiabatic compression and expansion. So first step is isothermal expansion. Heat's absorbed by the gas. So the gas is just the system right here. So we're basically, that's your QH. Energy goes into the system. Once that energy or that heat goes into the system, in this case it's 100 joules, then we have adiabatic expansion. Wait, so what would that be? Was that work on or by if it's adiabatic expansion? Does it work by the system or work on the system? Yeah, by the system. So in this case, the system, like you heated up this gas is going to, of course, move a piston. So it's going to do work on the piston. So you could say that this gas is doing work on the piston, or that the gas or work is being done by the gas. All right, I know it's weird, Adam, but like let us know if we can kind of think of it like I drew that box, right? So basically the system's pushing against something, so it's by. If you're pushing against, it's by. If you're pushing on it, it's on. That would be a way to think of it. But there's a bunch of different ways to kind of conceptualize it. We'll do it a bunch. Do it enough and it'll stick. That's the main thing. All right, so then we're basically, this is the work. This is getting the tires spin. We move the piston through moving differentials in a complicated system that we don't need to worry about. Makes the tires eventually spin. There we go, to get 20 joules. So after that has done work and basically moved the piston and made the tire spin, then we isothermally compress it. Remember, isothermal compression, the only way you can isothermally compress something, because when you compress, generally things get hot, is by giving off heat. So in this case, that heat is basically the exhaust pipe. It's the steam leaving out the back of the exhaust, which in this case would be about 80 joules. So this is a 20% efficient engine. This is a pretty standard, I think, for new engines. All right, and then of course after that, we just have to rework it back where we started. So you then adiabatically compress it, right? Do work on the gas to raise the temperature, so we can repeat the process and start right back where we started. So the main idea is just when you see the different terms, realizing what's going on, right? So isothermal expansion, right? So it's gaining heat. Adiabatic expansion, pushing against the piston. Isothermal compression, giving off heat. And then adiabatic compression, heating it back up. And so then we repeat that process of compression, expansion, back and forth and back and forth. And eventually you get the car moving pretty quick. So here's the thing to know, efficiency. So notice that I kind of just looked at this and was like, oh, it's 20% efficient. There's a couple different ways you could do this formula, but the main idea is, honestly, I think the easiest way to do it is you take the total input energy and you put over that the amount of energy getting out of it. So notice work, you get 20 joules, you had to put 100 joules in, so it's 20% efficient. Or you could think of it as take the total of 1 and subtract any wasted energy, so the percent wasted. So notice 80 joules was percent wasted, put that over the total, which of course was 100, thus 1 minus 1/8 gives you the same thing, 20%. Yeah, there we go, exactly. Output versus input. Chuck's got it great. That's, I think, the easiest way to think about it. But you can do it either way. That's the main thing. All right. If you are into screenshots, I suggest screenshotting. And then we're going to do one more example of this with the reverse for fridges, and then we just do questions for the whole class after this. All right. So refrigerators are just the exact reverse of this. I know the arrows look a little bit wonky. I'll kind of redraw these if the pen tool works, which it looks like it's working again. So the main idea is that now instead of having arrows this way, I'm going to draw this with bigger font. Yeah, let's make big arrows. So now we're doing this right here. So look at the red arrows. These are the ones that we care about. Forget the other ones. I might make this a little bit cleaner to make it pretty for you all. There we go. It's a fridge. There we go. So here's the fridge for you. So once again, you have to define the system. And so in this case, the system is right here. Do you know what gaseous systems we often use for refrigerators? Like what kind of gases we use? Yeah, Freon, Grant, exactly. So Freon's pretty common. If you have a really big like commercial fridge, this is more in food industry stuff, they use ammonia actually is pretty common as well. But for any kind of like home fridge, they'll use Freon because ammonia is too dangerous. If you get a leak, it can kill you. And so they only really let you use ammonia fridges when they're regulated. You actually have food regulators and inspectors coming in and checking it out. So Freon's a standard for both air conditioners and fridges for, you know, consumer use, I guess you could say. It's just safer. It's more non-toxic, I guess you could say. All right, so that's the whole idea here. Now notice what we're doing for this is we're basically taking two input sources of energy, right? So in this case, the food is what we have on the right-hand side. So notice that we're effectively sucking heat out of the food and thus heating up the Freon. Additionally, we're going to do work on this Freon. This is basically the energy. This is I'll call it the socket. This is when you plug this, your fridge only works if you plug it into the wall. And this is the part that comes from the wall. This basically runs the compressors, which makes sense because notice how it has work. So work, of course, would be compression or expansion. And this is when you ever hear your refrigerator turn on where all of a sudden it's like, it starts making noise, but it doesn't do it all the time. That's this right here. That's the work. That's the socket. That's the compressors kicking on. And it's actually compressing that Freon. And so it doesn't have to do it all the time because once the fridge is cold, it just stays that cold. But once it basically drops below a certain level or above a certain level, I guess, the compressors kick on and it basically works to compress the Freon. And we'll show you how that sucks heat out of the fridge. Cool. And so then what would this over here be then? So if that's the food, that's the socket, what's that going to be there? It's a type of heat because we see it's a H. Yeah, where's it go though, Grant? You're totally right. Yeah, that's the word I'm going for, Lauren. It's heat out the back of the fridge. You ever stuck your hand behind the fridge before? Well, what do you notice? It's supposed to heat out the back. Yeah, it gets hot. Totally, Rochelle. That's the thing. So all of basically what's pumping out the back of your fridge is it's sucking heat out of the food. Then you also have energy from the compressors compressing the Freon. It's a combination of those two energy sources is effectively pumped out the back of the fridge. So this is a non-spontaneous process, right? It's not your fridge doesn't spontaneously get cold. In order to make the inside of your fridge cold, it's going to take an input energy of the wall socket in conjunction with the heat that's actually being released from the food decaying inside your fridge, I guess you could say. And so it's basically driving a non-spontaneous process through putting work into it. In this case, it's the work from the compressor's socket. But so it's the exact same thing we did before. We're just reversing the order. So notice now instead of having an input where you basically have heat go in both directions, now we're taking input from two directions and putting it out into one. And so first you have isothermal expansion. The refrigerant absorbs heat from the food. One thing I want you to be aware of, though, which is you don't have to use Freon, but why we use Freon, is that you can take advantage of not just changing the temperature of Freon, you can also change Freon from a liquid to a gas. If you guys saw the actual Thermo 1 class, remember when we drew the chart where it had like temperature change, phase change, temperature change, phase change? You guys know what I'm talking about? Do you remember how it took an exorbitant amount of energy to actually vaporize things, right? When you think about the heat required to turn a liquid into a gas, it's massive. And so by using something like Freon that can exist inside the fridge as either liquid or gas, you can be converting it from liquid to gas, and that heat of transformation is going to be a ton of energy. So it's more than just heating up the gas, it's also doing phase change as well. It's just more effective. You don't have to do that, but you're going to get a much, much, much better fridge if you can have something that takes advantage of both temperature change and phase change. You think I'm not sure what you mean by F, Adam, but I think that's what you're talking about. Let me know if that makes sense, everybody. Oh, okay, cool. You're hurt. Gotcha. Cool. Yeah, I'll let him cover that one. All right, so we'll go through all the steps, but that's the main idea here. It's phase change and temperature change too. So first, isothermal, no change in temperature, right? Basically, the refrigerant absorbs heat from the food, so it causes it to expand. And then, of course, we turn on the compressors, right? The thing, which of course does work on the gas to raise the temperature, right? Adiabatic compression makes it super hot. Then that heat, of course, is going to go out the back of the fridge. That's your isothermal compression. Once again, if you are not changing temperature, then you must have heat entering or leaving. And then finally, we adiabatically expand it. Once again, gets back to low temperature and repeat the process. But once again, main idea is really efficiency in terms of order of operations. You're going to put energy into this to move heat from one place out the other. So you're pulling it out of the food, pumping it out the back of the fridge through the use of these compressors. And you've got the formula on the bottom. It's the exact same idea. Remember, the QC is the heat from the food. I'm going to move this so you can actually see everything on the bottom there. There we go. That's the socket being moved up. As we said, work was the energy from the wall, and QH is the heat released behind the back of the fridge. Whew. All right. Feel free to take a screenshot. We're going to spend the rest of class just doing questions from this point on. So it's basically half talk and shop, half doing questions. And so if you do have any questions about this before we get deep, let us know. But in the meantime, we're going to go through application of this. And you do not need to memorize this stuff for the test. Like, you don't have to know specifically how fridges work. You know what I mean? In terms of like which is QC, which is QH, and all that stuff. But the general idea of compressing, expanding, and alternating back and forth to move energy is huge. And there you go, Rochelle. Now your fridge works, and your air conditioner, and all the other things as well. Which is, well, actually, I'll let you. Normally I explain a couple more things. I'm instead going to let you guys answer some questions, and then I'll kind of give some more examples. Because there's a lot more I could talk about, tons of examples, but I'd rather kind of quiz you guys fresh and see how you do on all the passages, and then we can kind of explain as we go through. So we'll see if we can kind of figure it out as we go. All right, so I'll let you guys read this. I'm going to, if you haven't already, I do suggest downloading this Download Me guy, just because it is going to have the entire passage. You might want to re-reference the passage. It might not be on screen. While you're doing that, I'm going to bring up a poll for everybody to use. So we'll go through these in a sec. All right, pretty short, so hopefully that was enough time. What is this passage discussing? Or what do you think you're going to get tested on? What kind of stuff's like fair game, test day kind of stuff here? Oh, and actually, Adam, I saw your question in Q&A, and I want to talk about that, so I'm glad you brought that up. Yeah, we're talking about efficiency, totally testable, agreed. Steam engines, mostly what we're probably going to be tested on is one of two main things. Either, well, what do you think? What would probably be the big things we'll be tested on? Efficiency is one, and there's one other big one here. Yeah, honestly, Rochelle, just like the picture, the process, what's going on. Like they'll probably then like manipulate the picture somehow and say, what if you open this, close this, all that kind of stuff. How is it going to work? Yeah, exactly. It's kind of like just talking about the general idea of what's going on here. Generally, the picture, you got it. So efficiency and the image itself. The thing that Adam brought up that I do want to talk about, and it's basically the question was how like you kind of like suck the heat specifically out of the food. This is actually a major thermodynamic concept. Can you transfer cold? Can you basically get cold into your body? You cannot. There is only a transfer of heat, right? And so the whole idea is that if you ever have two different objects, we have a bunch of different types of heat transfer. So what are the types of heat transfer? Let's kind of bring this in right now too, because this is actually a can of worms, but there's a couple really big concepts here. Conduction, which is contact, right? Molecule to molecule sitting. Convection, which is the bulk movement of fluids, right? Fans or moving liquid type stuff. And then radiation is the last one, right? So that's actual electromagnetic rays. And so the idea is every object, unless it's at 0 degrees Kelvin, is actually radiating energy. Like right now, your body is radiating energy out of you. What type of electromagnetic radiation is emanating out of you at all times? Given that we're just humans and not, like crazy celestial, sun creature things. What kind of energy do we radiate? You can see us on certain kinds of cameras, right? Yeah, what do you call that? What type of radiation is that, Adam? Not ultraviolet, that would be infrared, exactly. Yeah. UV is way too high energy. That would be like even greater than visible, right? But so infrared is lower than visible light. Basically, it's just heat, right? If you look at, you can actually use infrared goggles and look around, and anything that is hotter than its environment will show up. And so the idea is if you put an object in the fridge and its temperature is higher than the environment in the fridge, it's going to be radiating infrared radiation to the heat until it's finally reached thermodynamic equilibrium with its surroundings. And so that's kind of the whole idea is like the way you suck heat out is just by putting it into a cold room, it's going to eventually equilibrate. It will suck all the heat out. But that's also why if you like cook food and you want to save it for later, don't put it in the fridge when it's hot because it's just going to make your fridge run a whole lot more to cool it down. Let it cool out to room temperature first on the counter, then pop it into the fridge, and then it basically will just be saving energy in the long run. Totally, yeah. I was going to say little tips to save yourself heating bills. You know what I mean? Cool. So that's a big idea. So we do constantly radiate. Exactly true. Infrared. Yes, paranormal shows talk about maybe like some other ghosts emit radio waves or something. I have no idea, but it's totally possible. I just don't know how ghosts work. But yes, probably something to do with paranormal shows. To be honest, I agree. All right, so that's the main idea with the energy transfer. Know your conduction, convection, radiation. Super huge, high yield stuff for test day. And mostly here, as we said, the things to focus in on is we have an equation for efficiency, so be aware of that. Right there. We want to know how all of this works. Notice that it is not possible to convert all the input heat into output work. We talked about that. There is no 100% efficient engine. It has yet to be built. Humans can't do it. Maybe someday we'll figure it out, but thermodynamics doesn't think we will figure it out. They think it's not going to happen. Cool. And then finally, we talk about the refrigerator at the very bottom. Notice once again, it's all about changing the refrigerant to a gas. So the liquid that circulates through the refrigerator changes to a gas. That's why Freon's useful, because you can vaporize it pretty easily inside a refrigerator. All right, let's do 2 questions. So let us know if you have questions on that, but let's knock this out. Put your answers in the polls. We'll spend the next 20 minutes just doing a bunch of these questions. So there was the equation we gave you earlier. I'm going to show you where we're at just because we're pretty split right now. It's not a very big group today. Also, we're a pretty small class. We only got about 16 folks. So a little torn all over, but we do have one leader, and that's B. I agree. It is actually B. Now, what makes B an better answer than D? Because there were a lot of votes for D, and I agree that makes sense because we do like to think of, basically that right there. What makes B better than decreased amount of heat output? What makes B better? Why is it better to decrease the exhaust and not decrease the actual input of energy? I mean, it's true it is smaller, but think about structurally here, though. We don't need to use math. Let's think structure here. So you need the input energy. What truly makes an engine efficient or not efficient is how well it utilizes that input energy, right? If you take 100% of your input energy and put it towards work, awesome, that's super efficient. But the only way you would do that is, as Ian says, is by having less waste. So it's more about diverting away from the waste and towards the work, not just decreasing the input, right? Because you can have billions of megawatt input, but as long as you get billions of megawatt output, that's still 100% efficient. Exactly. So it's diverting away from waste, Adam. That's the way to think about it. I like it. Cool. And that, yeah, exactly. All right. So totally true. So yeah, there's lots of ways to think about it, and this is my goal for today's class. It's not just memorize the equations. Think of examples. Think about how it works and see if you can apply it and be like, all right, well, it's kind of like this, so probably this answer is usually the best way to solve thermo questions, not straight math. All right, so I will clear this out. Once again, throw your answers in, and I will also bring up the picture so you guys can see it. This boiler is starting to boil. All the steam starts to come in. The steam enters through this intake valve, and then it basically hits this piston, and then makes this little turbine thing spin. And that's basically the work that it's doing is pushing against a piston or spinning a piston. I guess it's pushing a piston would make more sense, but basically it's making it do some work. And then we've got this exhaust valve, so the steam goes, we condense it, and then we can pump it back to the boiler and recycle the whole process. So if you want to make sure you get the maximum amount of work on this piston, do you want the exhaust valve open or closed? First of all, better be closed, right? Because if that exhaust valve's open, all your steam is going to leave, and it's not going to do work. So you can get rid of A because that says both would be open. Exhaust valve should be open. Get rid of D. So it's either B or D. And looking at your answers, we do have a lot more people going for B. I agree, because if the intake valve was closed, steam ain't getting in the first place. You got to let the steam in so it can do the work. And so if you want to get the most work done, let the steam in, but don't let the steam out, which is why we do have about 54% of you going for answer choice B. So notice that we don't need to use equations. We don't need to use even major constants from Therm to do this. It's like figure analysis, right? When you look at this figure, think about how it's actually working. How is this steam going to move, and how is it going to move the piston? AAMC loves stuff like this, and just heads up, did you guys know this is an actual MCAT passage? This is legit, not even our stuff. This is AMC stuff. For real. This is the kind of questions that they give you. This is older. This is pre-2015. You know what I mean? Yeah, you got it. So totally true. Like same concept for shell for sure. But it's still the same. And that's one thing I've heard from a lot of people from both the sample test and people who just tested. They thought it felt like AMC stuff. Like people would take it in the past. They're like, it honestly, like AMC has a very common theme to it. So if you're taking the, whether it's the practice test items for the sample test, whether you're doing the AMC question pool stuff that's now posted on your syllabus or these, it really is pretty straight. You know what I mean? It's more straightforward than you'd expect, I guess. I'm not sure if there's one on this was pulled from a full length. This is one of their outdated or their retired full lengths is where we took this from. So this was, but it's no longer. I think this might be in your, it might be in the AMC question pack. I'm not sure if they've used this one or not. But all you guys know what I mean when I say the AMC question packs, right? Does that make sense when I talk about that resource? Cool, yeah. Those are, so check it out on your syllabus. If you go to the AMC sample items, don't take the AMC sample test, save that for last, but they have a massive resource now. It's posted on your syllabus of actual AMC former questions. They have cars, chem phys, biochem. There's no psych soc because it's all old MCAT stuff. Yeah, I would use that sooner, Navina. If you're testing in May, I would start now. I would try to get through all of it before test day. I would actually put a higher emphasis on that stuff than QBank. Well, I would just make sure you get them all done. I would do all the AMC stuff, every bit of it, because they're the people who make the actual MCAT. You want to get used to that like style that I'm talking about, and this passage is a great example of like the AMC style. You want to be very kind of comfortable with the way that they bring up these kinds of questions, and even though there's a whole passage on Therm, the questions aren't necessarily making you use a lot of Therm to answer, and so they love that kind of stuff. So just really get comfortable with the resources, and I would do all of them before test day. Hit us up in Q&A if you want specifics for timing, when to do it. Let us know when your test day is. Let us know what your questions are. We can kind of help you finagle a schedule and all that stuff in Q&A too if you have any questions. So hit us up. All right. Meantime, though, let's do the next question. We'll finish off this passage and then we'll do most of the next one, at least enough to talk about it. Or at least the map or the outline. Talked about this when we talked about the fridge too, because notice we're talking about the refrigerant specifically. So this is like the Freon, right? Or ammonia. I spelled Freon wrong. That looks weird. So we have two different categories of terms here. We have heat of either vaporization or fusion and specific heat. So what does specific heat refer to specifically? Perfect, Adam. It's a great way to say it. So calories needed to raise temperature. Let's do one thing that you have to memorize. What is the only specific heat that you have to have memorized for test day? Water, which is, as Adam says, 1 calorie per gram Kelvin. Or what's that in joules? You gotta know joules too. 4.184. You could honestly just say 4 for the MCAT. You can round, as you know, quite a bit. But yeah, it is 4.184 to be very technical. Also, that'd be joules per grams Kelvin. Also, interesting thing to know about water is that 1 gram of water is equal to 1 milliliter water, which is equal to 1 cubic centimeter of water. It's as if we based the entire metric system on water, because we did, because water's awesome and very important. So that's kind of the neat thing about water in general. All right, so remember, what is more effective at moving heat? Was it the phase change, or was it the actual changing of the temperature of the refrigerant? We talked about why Freon and ammonia are so good. It's all about the phase change. And this one is passage-based as well. It specifically told you that heat was absorbed from the refrigerator when the liquid that circulates through it, this is the refrigerant, changes to a gas. And so if we're talking about the liquid being changed to a gas, what phase change is that? Specifically, it would be the heat of, as we got about 50% of you saying, vaporization. A, Grant, you got it. So that would be that. And so also remember that your heat of phase change, so this would be for both A and B, use this general formula. For C and D, what's the formula for the specific heat phase change? So C and D would use the formula Q equals, nice, MCAT, MC delta T, you got it. Whereas for the heat of fusion or vaporization, that would be your M sub L. And you don't need to memorize the delta H terms for anything. They'll be given on test day. Cool. All right, tying in some content as we go. Let's keep on moving. Question number 4. Ooh, we did talk about this today too, and I'll bring up the image so you guys can see it. %100% correct so far. Nice work. All right, so if we want to change steam to water in the condenser, you want to make sure that it's going to cool it down. So which of these would actually cause an increase in temperature to surround the condenser with? Two of them would. A and B, actually, I would say. Why would A and B actually cause an increase in temperature? Because if it's steam, that means it's by definition at least 100 degrees Celsius, right? Water boils at around 100 degrees Celsius, so you're surrounded with steam, we're surrounded with something that's pretty darn hot. So we don't want to surround with something hot, we want to surround with something cold. Exactly. So what's going to be more effective? Either stationary water or circulating water to cool down that condenser. And everyone's going circulating. What is the key word on why circulating works best? We talked about this before. It's one of the types of heat transfer. Circulating water means it's using not just conduction, but also convection. Yeah, it's due to convection. It'd be convection cooler. So remember, this is like the way convection ovens work is you just put a fan in the back of the oven, and if it blows air over the food, it's basically using the bulk movement of hot air to cook it even faster. It's the same thing. I don't know if do we have any athletes? I talked about this in the last class. But anyone a collegiate athlete and ever been forced to go into the hot whirlpool? Yeah, you got it. So usually it's not just a bath, but they actually turn on the cycle, so it's actually moving cold water, right? Really freaking cold. And the whole idea is if you have that circulating cold water, it gets you colder so much faster than if it's stationary cold water. It's really, really, really effective. And so that's the whole thing by having cold moving fluids. It's the same reason why if anyone's ridden a motorcycle before, even if it's like 50 degrees out and you get on a motorcycle, you're freezing. It's so cold because of the wind chill atom, exactly. By having that cold, even though it's only 50, having it moving over you, it just keeps stealing heat away from you, and you get really cold really fast. So that's like, it's really actually cold on motorcycles, even when it's not that cold out. But yeah, it's the wind chill effect. You got it. All right, let's do number 5. Also information pulled from the passage, but we talked about it as well. And the answers are actually looking pretty good. Actually, I'll give you guys, I'll be honest, you guys are totally torn between A and B. So we're choosing either A or B across the board. And notice if you look at the two, the only difference is that B has or equal to. What did we talk about with in terms of heat transfer and work being done? Remember what we didn't have? There was no such thing as a, you got it. There is no perfect conversion. There is no 100% efficiency. Like you're gonna lose some energy in terms of the transfer. And this is actually the number one thing that comes, like if you want to talk about like energy crisis in the future of, like power shortages and all that kind of stuff, the real issue that we have is actually two things. Converting energy from one form to the other. So think about like the way that power plants work. We're actually creating thermal energy through boiling a bunch of coal, which then boils water. The boil creates steam. The steam turns turbines. Then that finally creates, the moving magnets, which creates your electric field and current. And it's the conversion of thermal to electrical. You lose tons of energy, crazy amounts of energy. And so it's like what I hear is if we could really somehow create a direct conversion of just electrical to electrical and not have to use energy blowing stuff up first and heating stuff, you'd actually could use a lot lower energy input and still get the same amount of output without having to convert between forms. That and actually transferring energy across long distances, like the high energy lines, like being sent in the air across states, we lose a bunch of energy from resistance in those wires too. So those are kind of like the two main problems right now is the conversion factor and the transfer factor. And if we can solve those two, we will be basically golden in terms of energy crises of the future. You got it, Grant. So this is not considered theoretical circumstances. You got it. So, I mean, theoretically, maybe we could someday do it, but according to the laws of thermodynamics, you won't get perfect conversion if you're converting between things. Because notice here you're using thermal energy in doing work, so you are already doing like conversion between the two. If that makes sense. And also, it was passage-based. It told you explicitly in the passage that it's always less than. So you could also argue that's a passage-based question too. Cool. For sure. All right, we'll just finish this passage. So we got like 3 more questions to go. Basically, Rochelle, yes, AMC loves pseudo discretes. Very much so. It's their bag. It's their jam. Oh, and this is exactly what we're talking about. So energy transformations. So we know it's starting off as heat, so you can get rid of A and B because we said it was definitely heat. So it's either heat to electrical or heat to mechanical. And you got it. We have 100% correct, so I don't even talk about it. You guys are right. It's mechanical because specifically we're talking about compression expansion. It's actually moving a piston. So that would be much direct work in terms of like force and application of force over distances and stuff like that. Oh, Lauren, I don't know how to make gold stars. I think I broke it last time I tried. I think one of the other teachers probably knows how to, but I know there's a way to do it. I think it's a glitch in the system, though. I don't really know how it happens. Whoa, look at that. Weird. So weird. They just start appearing sometimes like that. No idea how that happens. It must be Chuck. All right, let's do the next one. Oh, man. Chuck does these things. All right, this one's getting into actual concepts, so I'll let you guys think about this for about a minute or so. All right, that's most of it. It's true, it was. All right, most of us have voted at this point. This is getting into the actual guts. So notice most of those are pseudo-discretes. This is kind of getting into more what we're talking about. So if you want to do work on what could be done to the gas in order to condense it to a liquid, so if we want to condense it to a gas to a liquid, what do you want to be thinking about first? What do you need to do to it to basically turn it into a liquid? What do you need to... Yeah, you need to, well, 2 things. Do you want to put energy in or energy out, first of all? Energy out, exactly. So there's 2 ways you could say either drop temperature, I like how Adam and Elizabeth are saying that as well, or you could suck energy out. So would that be endothermic or exothermic to suck energy out? Nice, exothermic, right? To use the Gen Chem terms that we haven't really brought up too much. Exactly true. So nice, right off the bat, we can eliminate 2 because notice A and B say the opposite. That says increased temperature. No, that's going to not turn a liquid into gas into liquid. That'd be the opposite, right? So get rid of A, get rid of B. It's going to either be C or D. So it looks like either decreasing volume at constant temperature or decreasing pressure at constant temperature. One of these we talked about actively needing to have heat leave. And which one's actually, what's the other name for the correct answer? We do have most people going for it. What type of compression is it? Because you are right, 72% saying C. That would be type of isothermal compression. Because remember, when you have isothermal compression, in order to compress a system and have it not get hot, you have to have heat leave. So effectively, you're making heat leave. So the 2 correct answers would either be to look for something with dropping temperature or heat leaving. And C is exactly isothermal expansion. Sorry, isothermal compression, thus exothermic, thus heat leaving that system. All right, so we'll knock out another question or 2. We'll call it quits. All right. We have most people voting, but we're really torn on this between A, B, and C. So first things first, we're talking about the refrigerant, right? So remember, the refrigerant talked about what phase change between what two phases, first of all. Between liquid and gas, exactly true. So we don't need to care about freezing point or freezing point because that's not dealing with liquid to gas. Boiling point is. And so remember, regardless if you're talking about gas to liquid or liquid to gas, it's the same, right? It's just talking about different directions, but it's still boiling point. You can call it condensation point or boiling point. It's the same temperature. All right, so now where do we want this thing to boil again? To turn between gas to liquid and back and forth? Inside of a refrigerator, first of all. And so if you want something to boil inside of a refrigerator, how high should that boiling point be? Pretty high, or? Yeah, Adam, pretty darn cold. You want to boil inside a refrigerator, it needs to have a relatively low boiling point. In fact, I don't know Freon's boiling point, but ammonia, the one we use in commercial fridges, its boiling point's like negative 30 degrees Celsius. Negative 30 degrees Celsius boiling point. And so you got to have very, very, very low boiling points in order for these to actually, like boil inside of a refrigerator. Good way to think about it. All right. Let's do one. We'll do last question of the day. We're last channel session. Let's do question 9. We'll call it quits. I'll clear out let us know if you have questions on that. We can also hang over late and answer questions in Q&A as much as you guys want, but we pretty much always assign passages as homework, so we'll do the same today. Awesome. We're doing really well on this. So I'm gonna end with an example today. So what would happen if you were to take your air conditioner and instead of putting it in the window or outside as the central airs do, and you were to put it in the middle of your living room? So what would happen if you plugged in an air conditioner, not in the window, but in the center of the living room? Would it still blow out cold air? First of all, it would. It would blow out cold air. But what else is it going to blow out? No, it'll blow out cold air. It actually will blow out cold air. But it's going to blow out hot air out the back of it. You got it. So it still is going to create a cold air system, but in order to create that cold air system, it has to create an even hotter system blowing out the back. That's why you got to put the air conditioner when it's in the windows. And I don't know if you've ever lived in an apartment building where there's a bunch of AC units on the roof, but if you ever go up in the middle of the summer when all those ACs are running on the roof, it's like a death trap up there. It's so freaking hot. It's just all this heat blowing out all over the place. It's terrible. But so the whole idea is you do need to have a total increase in energy in order to move heat. We had most people going for A. We were kind of split across the board. But you got it. Like, the whole idea is that in order to create a cold system, it's thermodynamically, it's not spontaneous at all. So you got to actually put energy in to make that happen. So the heat that's blowing out the back of the AC unit is both the heat that it's sucking out of the house, right? Because it's absorbing heat where only heat moves, as well as the heat from the socket in the wall. Like sucking energy out of that. So cool. So take-home point for that is don't ever run the AC unless you put it in the window. Otherwise, you're just going to cause problems. It'll actually heat up the house. It's true. All right. I had a lot of fun. I hope you guys had a lot of fun today, too. Ending a minute before the hour. It's the very last session of the day. If you do have any questions, let us know. We'll be hanging out in Q&A. We got recaps. There is a passage that's homework. I want to give you a heads up. It's basically all pseudo-discretes. It's very straightforward as well. But do let us know if you have any questions. All right, you're all very welcome. I will see you all for future channel sessions.